Hey guys, welcome back. This is Physics Circuits Part 3. We're going to do a little bit of review with resistors, and we're going to apply Ohm's law to circuit situations. So if we have a meter, it can measure multiple things. If we remember, if we want to measure the voltage, we measure that across a component. If we measure a current, we're going to measure it through. All right, so adding up resistors. If I have these four resistors that are all in series, I'm just going to add them together. So I have 10 plus 50 plus 20 plus 30, which ends up being 110. These are all in parallel. If you have two resistors that are in parallel, the replacement resistor, the equivalent resistor, is 1/2 the original one. Now I have four of them that are all in parallel, and they're all 40. So if I put this in my calculator, I would get 10. These two are in parallel, and they're the same, so they can be replaced by a 5, and then that new 5 would be in series with the 10, which would add to 15. These two are in parallel. They're both equal to 20. That means they can be replaced by a 10 ohm resistor. These two are in series, so they could be added together. 25 plus 25 is 50. Now I have a 50 in parallel with the 50, and again, they're the same. You just take 1/2, 25. These two are in series. I can replace them with an 8. These two are in series. I can replace them with a 13. Then I would have to do 1 over 8 plus 1 over 13, which is 4.95. And then 4.95 plus 4 would be 8.95. All right, if I want to combine these to get a 3 ohm resistor, I have 4 12 ohm ones. If I put 2 of them in parallel, that would make it 6. If I put 3 of them in parallel, it would make it 4. If I put 4 of them in parallel, it would make it go down to 3. So I would just have 4 in parallel. If I want them to add up to 18, I would have a 12 in series with 2 12s in parallel. And again, a 12 and a 12 in parallel would be a 6. So a 6 plus a 12 would be an 18. If I want them to add up to 30, I would have a 12 and a 12, which would add to 24. And then I would have a 12 in parallel and a 12 in parallel, which would be 6. 24 plus 6 is 30. And if I want them to add up to 48, I would just put them end to end, because 12 times 4 is 48. So here's a picture of a series. We have the current is the conventional current, so the flow of positive charge. There's one single path through all of these resistors. When things are, so in this case, the same current goes through each one of these. And so I can say that current is the same in series. They share a path. Now there's only so much pressure from this battery, and that pressure is shared by all of them because it's one after another. So I is going to be the same. So the current through the first component, I1, the current through the second component, I2, the current through the third component, I3, is all going to be the same value. The voltage, the battery only has so much, and each of them use up some of it. So my V is going to be equal to V1 plus V2 plus V3. If I have parallel components, the current gets split. So the current leaves the battery, and then some goes this way, some goes that way, some goes that way. And so that means that my I is going to be equal to the sum of them. So the current has to be conserved. But in this case, each one of them has an individual path to the pressure. So they all get all of the battery. They all get all of that voltage. And so in parallel, voltage is the same. I don't know why I put plus, it should just be equals. I'm thinking about lunch, I think. Hungry. So in parallel, voltage is the same. So in series, current's the same. In parallel, the current is the combination of the partials. I always think of these two things as ISVIP, where I is current, is the same in series, and V is voltage, is the same in parallel. Current is conserved. If you remember from the last section, we didn't get charge out of nowhere. The charge was also conserved. Current is charge per second, so current needs to be conserved. So current doesn't get used up, charge doesn't get used up. So in our picture here, the blue arrow, some goes down as a red arrow, some goes as the green arrow, but the total, which is both coming out of the battery and going in the battery, would be the sum of those. So in series, each of the components will use up some of that pressure, some of that voltage. In parallel, they would get all of it. So here's a picture, and this shows us what our potential is. So if I go from D to E, I gained 12 volts of potential. I go through my wire from E to A. So this is 0 ohm resistance for a wire, as far as we're concerned. Then when I go from A to B, I need to lose some of this voltage. So I lose 7 volts, and that leaves 5 volts for this one. And then I lose the last 5 volts, and then I end up through the wire again. So no loss at all here, back to the other side of our battery. Keep in mind, the battery has no idea what resistor is first. So if I move the 400 ohm resistor after the 290, it's still going to lose 7 volts on the 400 ohm resistor. That battery feels all of those components at once. It doesn't feel one and then feel the other, right? All of these things already have electrons in them before you hook up that battery. And you're just causing them to move. So this is called it's one of Kirchhoff's loop rules, and the idea is that the sum of the changes in the potential around a closed loop is 0. So all the potential gets used up. All right, so to solve these problems, we're going to make a V equals IR chart. Then we're going to find our total resistance, our total current, and our voltage. And we're going to remember that current is the same in series and voltage is the same in parallel, which we know is ISVIP. So here's our chart. So for each one of the resistors, they'll have a voltage, they'll have a current, and they'll have a resistance. All right, so I'm going to plug in my values here. So all of these are attached in parallel. If I look at ISVIP, it tells me that voltage is the same in parallel. So that means that each of these is going to get 24 volts. what would this look like? For some reason, I didn't see that. We would have 24 volts. Each one has an independent path to the 24-volt battery. All right, so I can get the current through this one because I know that it's going to be an ideal conductor, and so I can use the equation that is derived from Ohm's law, but is not Ohm's law. So I1 is going to be V1 over R1, which is going to be 24 divided by 3, or 8 amperes. I can do the same thing for the second current. Which is going to be 24 divided by 5, which is going to be 4.8 amperes. And then the last one would be I3. That's going to be V3 over R3, and that's going to be 24 volts divided by 8, which is 3. And so all of the current comes out of the battery, all of the current goes into the battery, and then it splits. But all of that together would be that total current. So the total current is going to be 8 plus 4.8 plus 3, which is going to be 15.8 amperes. And then I can combine these resistors because they're all in parallel as 1 over 3 plus 1 over 5 plus 1 over 8, which I think is 2.4, but I'm just going on memory, and I should actually put it in the calculator and get the answer. Nope, 1.5. 1. $1.52. All right, now they're in series. So that's what this is going to look like. My total voltage is 24. And again, the order of these doesn't matter. The one that's going to get the biggest voltage is the biggest resistor. So in this case, it's the 8 ohm. All right, in series, it's easy. You just add the resistors together. So I have 3 plus 8 is 11 plus 5 is 16. Now I can get my total current because I know that my total voltage is equal to my total current times my total resistance. So my total current is my total voltage divided by my total resistance, which is going to be 24 divided by 16, which is 1.5. And what does ISVIP tell us when we have things in series? That current's the same. So the same current is going out of the battery and going in the battery, and that means that all of these get 1.5. And then I can solve for the individual potential drop across each of the resistors. So V1 is equal to I1, R1. V1 is going to be 1.5 amperes times 3 ohms, or 4.5 volts. R2 is going to be equal, V2 is going to be I2 times R2, so it's still 1.5 amperes. R2 is 8 ohms. 1.5 times 8 is 12. And then I can look at this in two different ways. R3 has to get the rest of the potential. So I started with 24. I lost 4.5 and I lost 12. I'm left with 7.5 volts. Or I can take 5 times 1.5, which is also 7.5 volts. So all of the potential needs to get used up in the entire loop. All right, now I have a battery in series with one resistor that's in parallel with 2 other resistors. So combination 1. So the first thing I want to do is find my total resistance. So can I combine any of these resistors to make my life easier? Yeah, I can combine these two because they're in parallel. And so I would take 1 over 8 plus 1 over 10. Which gives me 4.4. Repeating. Where does this go in the chart? Nowhere. Because it's not real, right? It's this imaginary resistor. But now I could replace these two with this one. And so I know that my total resistance is just going to be the 5 plus the 4.44. And so I end up with, move that out of the way, 9.4 or 9.44 is the total resistance. Now I can get the total current. So that should tell us something. So I total is going to be V total over R total. And so this is 24 over 9.4, which I'm guessing is going to be close to 2.5. 2.55. So I'll say 2.6. All right, now I'm going to think about ISVIP. ISVIP tells me that the current is the same in series, the voltage is the same in parallel. So what do I know? I know that I start with 24 volts, and I know that my current coming out of my battery is 2.6 amperes, and I know that the current going into my battery is 2.6 amperes. Is anything in series with this current? And the answer is yes, the first resistor. The first resistor and the battery are both in series. They share a path. So that means that this one gets all of the current. It has to go through that resistor. And so my voltage is going to be 2.6 times 5, which is 13. So I times R. Now, I started with 24 volts. Change colors on you guys. Right? I have 24 volts. When I went across this resistor, I lost 13 volts. Resistors cause voltage drops. They dissipate energy. So now if I had 24 and I lost 13, I'm left with 11 volts. So these, I have to lose 11 volts from there to there. Now, do each one of these get 5.5 volts? No, because each one of those resistors that's in parallel provides a path. And over the entire path, you have to use all the voltage. So I need to drop 11 volts on this path and on this path. And so I can get I2 by taking V2 over R2, which would be 11 over 8. If you had a better physics teacher, he would pick rounder numbers, so we wouldn't have to be dealing with all of this. I got 1.4. And there's two ways to look at this. The current needs to be conserved. So that means that if I started with 2.6 and 1.4 went the one way, that means that 1.2 has to go the other way, because these two numbers together have to equal that. Or I could do that I3, as I write V, I3 is going to be equal to V3 over R3. And this is 11 volts over 10 ohms or 1.1 amperes. So why aren't these exactly the same? Well, rounding. That's why I said if you had a better teacher, he would have made it so you didn't have to round and they would work out better. I rounded here to 9.4 and I rounded there to 2.6. And so that makes it, it's not a huge difference though between what, if we're talking about 1.2 and 1.1 amperes is not that big. All right, so series. They share a path, current, parallel, multiple paths, same voltage. Adding resistors in series, you just add them. In parallel, we have to do the 1 over. Again, you can see I'm adding more things, but we're going back and reviewing, so we're clear on what we're doing. The equation for Ohm's law is V equals IR. To solve Ohm's law problems, you're going to make a chart. You're going to find your totals, and you're going to use ISBIT. So current's the same in series. Voltage is the same in parallel. And you'll have some students tell you that ISBIT stands for I suck at Verley's physics. It doesn't. It stands for current's the same in series, voltage the same in parallel.